Okay, so we're going to finish this section off by first mentioning a note here, which is really just going to re-emphasize something that we've already said on the previous page, but we're going to say it in a little bit more of a complete manner. And then we'll finish off with an example. So the first thing we'll say is this note here, which says that the effect of a column operation on a determinant is the same as the corresponding row operation. So I mentioned this on the previous page, but let's go through this in a little bit more detail. So remember on the second page where we went through the effect that each row operation has on determinants. Let's just quickly run through this first one again. If you start with a matrix A and you perform the operation that you see here, so interchanging any two rows of the matrix A, and you let the result be denoted by B, that's really another way to interpret this notation. Or if you can carry A to B by performing the operation of interchanging two rows, then the determinants of A and B are going to share this relationship. The determinant of the matrix you end up with is exactly the negative of the determinant of the matrix you started with. So in other words, interchanging two rows changes the determinant by a factor of -1. So what this note is saying underneath is just saying that, well, column operations are the same thing. So if you interchange two columns, same thing. You change the determinant by a factor of -1. The second type of row operation you could do that we looked at was you can multiply any row by a non-zero constant, and for lack of anything else to call it, let's call it k. That's what I used here. You can call it anything you like. But what this says, if you multiply a row by a non-zero constant k, you change the determinant by exactly a factor of k. So if you want to phrase it carefully, if you start with the matrix A, you multiply any row by a non-zero constant k and call the result B, then the determinant of B is going to be k times the determinant of A. That's the relationship. So same thing with columns. If you multiply a column by a non-zero constant k, well, you're going to see the same thing. The determinant of the result is going to be k times the determinant of what you started with. So multiplying a column by a non-zero constant k changes the determinant again by exactly a factor of k. So it's the same for rows or columns in this case. And then the last type of row operation, the elementary row operation you could do, is you can add one multiple of one row to another. And the note we made at the bottom here says that, well, that actually just has no effect on determinants, which is really convenient actually, and it may be a bit surprising too. But if you add or subtract a multiple of one row to another, you don't change the determinant at all. I'm saying with this note here that it's the same thing for columns. We took advantage of this on the previous example, but if you add a multiple of one column to another, you have absolutely no, that has absolutely no effect on the determinant whatsoever. So it makes your job easier if you're doing those operations because you don't have to keep track of anything because there's no changes being made. Okay, so that's what this note means. If you ever want to perform a column operation while computing a determinant, just ask yourself what effect would the corresponding row operation have? And that's exactly what the column operation is going to have. Okay, and now we will finish the section off with another example. So again, it's a 4x4 matrix. This one won't work out quite so nicely as the previous one. So this one takes a few more steps to evaluate. But the purpose of this example is to show you that you can actually use all of these tools that are at your disposal on the same example. You don't have to pick one method and carry it through all the way. Like you don't have to just strictly choose cofactor expansion or strictly choose row operations. Like once you start performing row operations, you don't have to carry it all the way to upper triangular or lower triangular form. You can just go part way along the way until you're satisfied that the idea of doing cofactor expansion isn't too intimidating by that point, and just dive right in part way through. So that's the purpose of this example, is to show you what I mean by that. So we're going to find the determinant of this matrix B. So the determinant of B, well, first step is we'll just write it out because we're going to have to do some work on it. So I'll go ahead and do that. The second row, the third row, and the last row, 3, 7, 5, and 3. Okay, got it. So what are we going to do? Well, you could go ahead and start performing Gauss-Jordan elimination and get this into upper triangular form. Or you could do the following, which would be nice because it avoids fractions, and it also has the effect of introducing a bunch of zeros. Because usually if you're doing Gauss-Jordan elimination, you need to get a 1 up in the top left corner. And that's not really going to be strictly mandatory here, because we don't need to get it into reduced row echelon form, but we just want to introduce a bunch of zeros to make cofactor expansion simpler. So how about we just take advantage of this 1 here in the second row and use that to clear out the entry above it in the third row, the 3, this 2, and this 3. We can clear out all those entries, but we can use this 1 to do it. And just by adding, subtracting multiples of row 2 from each of the other rows, which that won't have any effect on the determinant, which is always nice. So let's do that. We'll take row 1 and replace it with row 1 minus 3 row 2. Then we'll take row 3 and replace it with row 3 minus 2 row 2, because that'll have the effect of making this 2 into a 0. And then lastly, we'll take row 4 and replace it with row 4 minus 3 row. Oh, not row 2, or not row 4, pardon me. This should say row 4 is going to be replaced with row 4 minus 3 times row 2. I'll just scratch this whole term out and fix it afterwards. 3 row 2, like that. Okay, so let's do that and see what happens. So the first row, 3 minus 3 times 1 is 0. 5 minus 3 times 2, that's going to be 5 minus 6. Here we've got negative 2 minus 3 times negative 1, that's going to be positive 1. 6 minus 3 times 3, that'll be 3. So that's our first row. Second row won't change, right? 1, 2, negative 1, and 1. Now the third row, we're going to have 2 minus 2 times 1, which is 0. 4 minus 2 times 2, again, is 0. 1 minus 2 times negative 1, that's going to actually give us positive 3. Then 5 minus 2 times 1 is going to give us positive 3 again. So that's what we end up with for that row. The fourth row, we're again subtracting row 2 twice. So subtracting row 2 3 times. So we got 3 minus 3 times 1 is 0. 7 minus 3 times 2, that's going to be 7 minus 6, which is 1. We got 5 minus 3 times negative 1, that's going to be 5 plus 3, which is 8. 3 minus 3 times 1 is going to be 0. So that is what we end up with. And really, now we can say, okay, are we in upper triangular form? No, far from it still. But we have gotten to the point now where the first column only has a single non-zero entry. So if we were to perform cofactor expansion along the first column, we would only have to compute one 3x3 determinant. So we would effectively be reducing a 4x4 determinant down to a 3x3 determinant in one step. So that's why it's advantageous to do this. So let's go ahead and do that. So if we do cofactor expansion, pay attention to the signs corresponding to each entry. Start at the top, you have positive, negative, positive, negative. Well, the only one that has a non-zero entry is the 1, and that occupies a negative location. Right, so our first term here, that is a non-zero term, is going to be negative 1 times the determinant of, well, it's going to be multiplied by the minor corresponding to this entry here. So cross out that row and that column, and we'll have negative 1, 1, 3, 0, 3, 3, 1, 8, 0. And here's the point, right? We started off doing some row operations. Then we got to the point where we had a really nice column to do cofactor expansion along. So we did cofactor expansion, and now we're here. Do we need to use cofactor expansion to finish this off? No, we could do column operations or row operations, or we could do cofactor expansion if we wanted to. So you can mix and match your approach as long as you follow the rules carefully and pay attention to what you're evaluating and pay attention to the effect that whatever row operations or column operations that you do have on the determinant that you're calculating. As long as you keep all your books in order, you can mix and match the strategies. So how about we do another row operation? How about we add row 1 to row 3? That'll turn this into a 0, and then we'll have another really nice column that just has a single non-zero entry. So we'll take row 3, replace it with row 3 plus row 1, and that's going to give us negative 1. We'll leave the negative 1 outside. First row won't change, negative 1, 1, and 3. We've got 0, 3, 3. And then our third row, we're going to end up with 0, 9, and 3 if we add the first row to it. So now the first column is looking pretty good again, so we can jump into cofactor expansion and do cofactor expansion along the first column. So let's do that. So we've got -1, and what will we have? We'll have, well, we've got -1 times the determinant of this 2 by 2 matrix here, right? So it'll be -1 times the determinant of 3, 3, 9, 3, and that's the only non-zero term because the other two entries in that column are 0, so we can close that off. And then what will happen next? Well, these two -1s are going to cancel, so we really just have a determinant of 3, 3, 9, 3, which that's a 2 by 2 determinant now, so we can go ahead and just use the formula, right? This is going to be 9 minus 27, which is finally going to just give us -18 if you work that out. So that was an example of kind of mixing and matching strategies. We did some row operations, then we did a column, or we did cofactor expansion on a column, then we did another row operation, then we did a bit more cofactor expansion. You can mix and match these strategies. We could have done column operations at some point too, as long as you're careful and you follow the rules and pay attention to what you're doing and the effects that it's going to have on your answer. You're good to go. You can use a mixture of any of the strategies in however way you want.